Okay, so I think it is working. Is it recording? Yeah. Okay, so today we're going to be talking about action potential and resting potential. Basically, you're talking about the neuron firing, okay? The neuron firing and impulse. And for that to happen, now, as I said before, I am kind of expecting you guys to have watched that video that I put on Edpuzzle. So if you have not done so, please make sure you watch it. By the way, I'm just asking you guys, how do you guys call this in English? Like, using paper to fold up. What? No, well, not quite. I'm using elastic band and trying to shoot it too. How do you guys call that? Isn't slingshot like something you have to hold and has a Y bar and then you pull it? No? Okay. I learned this kind of thing in a different language. So in this case, I don't know how it's called in English. So in some ways, why am I talking about this? Because essentially, action potential is very, very similar to this idea. Okay. Now, in order for this bullet, let's just call this the bullet, to fire, you have to pull this thing back, pull the elastic back for a certain part. Okay. This elastic have certain tension. Okay. So the tension is very much like that resting potential that we were talking about in the video. Okay. That resting potential of how many millivolts? For those of you who watched the video, help us out. Negative 70 millivolts. Okay. So minus 70 millivolts. Now, if I release the grip just by a little bit, it's still not going to fire because I'm still holding it tight enough so that the force of me holding is still greater than the force of the elastic band trying to launch this, right? So I have to release my grip on this bullet just enough so that I'm not holding it hard enough for this bullet to shoot out. Once I release the grip like so, this bullet would fire, and it is a all or nothing kind of a scenario, right? So the bullet's fired, and I would not be able to shoot another one until I get make another bullet and reload it and pull back. So there is a period of time of, what's that period of time you cannot fire another nerve impulse? It's a definition word that I asked you guys to look up. Sorry, an R. Yep, refractory period. Okay, so we're going to talk about that. The reason why I'm using this is just to show you a little bit a different way to see how this process works. In some ways, yeah, I do archery, but I also realize bringing a bow and arrow into class to demonstrate that might not be legal, so that will work. Okay, so let's look up here. So right now, in this illustration, let's zoom in a little bit. So this is basically the surface of a neuron, or the axon part. What's the charge difference? When the membrane's at rest, it's ready to fire, but not quite. What's the charge difference between the membrane? Come on, someone say it. Yes. Yep. So it is more positively charged on the outside and more negatively charged on the inside. Okay. Now, keep in mind, the positive and negative we're talking about in relation to each other. Compared to the inside of the membrane, is more positively charged outside, okay? Just like I'm relatively tall, but if I'm standing next to someone who plays in NBA, chances are I'll be short, relatively speaking, okay? It's comparison. Okay? So now, when it's at resting potential, sodium is in high concentration on the outside, sodium ion, and potassium ion is in high concentration on the inside. Yes, they're both positive ions, but there are other ions in there that we're not going to be concerned about. And again, also, we're talking about relative charge, okay? Now, this is not shown here right now, but there is something that is maintaining this charge or this concentration gradient. What is it? It's an old friend that we saw back in Unit 1. Sodium potassium pump, thank you. So sodium potassium pump, how many sodium to what direction? Yes. 3 sodium ion out, and how many potassium where? Yes. 2 potassium inside, okay? So hence, you have way more sodium outside and potassium inside, okay? In the video talk about those leak channels, okay? And same thing here too. We're not going to be focusing on that right now, okay? We're not going to be focusing on that right now, okay? So this is just the resting potential. So this part, the membrane is ready to fire, but nothing have happened to it, okay? Now, just going to remove this part here. I'm going to show the potential charge. So I'm going to give this neuron a stimulation, okay? Depending on what kind of neuron it is, it will rely on different types of stimulation. Oh, so I'm pausing it right now. So what is the negative? Sorry, I kind of said it out loud already. So the resting potential is about minus 70 millivolts. Okay, so down here, that's the resting potential is at minus 70 millivolts. Now let's pay attention to what happens when the stimulus hit that section. Okay. Okay, so what happens? Let's scale back a little bit. Let's turn back time a little. So before it peaks, what's going on? So before it peaks, what happened? What is going where? Yes. Okay, so but which one go where first? So if you look here, what is going where first? Yes, good. So the sodium, so if you look here, this is the sodium gated channel. So the sodium gated channels are open. So the sodium are rushing in from the outside into the membrane, okay? So as you can see on this graph, it is climbing up. But these potassium gated channels are not open yet. So there's no real movement of potassium ion, okay? So when that graph is moving up, it's just sodium ion rushing inside. Once you hit to the peak, now at this point, if you look, the sodium gated channel, you have this little thing that closes it, that blocks it. So there should be no more movement of sodium ion moving. But you do notice that the potassium gated channel are opening up. So potassium ion is going where? Going outside. See, it's decreasing and going outside. So it's moving out. Okay, so that is the time when this whole line is going back down. The graph is going back down. Question so far? By the way, what's happening here? Why is this so low? Why is the membrane potential so low? It's less than the resting potential. Why was that? Yes. It released more than it originally has. Why did it release what more than it originally has? Good. There is still more potassium leaving than it originally have. Hence, it is still very low. But why is that? The video said it. Yes. That causes the hyperpolarization. But what happened that causes sodium more to leave, hence hyperpolarization? Which pump? The other one. So it takes longer because potassium is the one that's leaving, right? So let's just zoom back in time, scale back in time. Hold on. So if you look, the sodium gated, oops, what did I touch? So sodium gated channel is open. Now it's still maintained open, and by that time it's pretty low already. It kind of go below that during that hyperpolarization, it's still opening. Okay, so there's a delay in terms of when that. See, it's not until like at this point where it's hyperpolarized that this sodium gated channel is close. Do you guys see that? So now at this point, the sodium and potassium gates, they're both close, but then something is happening which causes the membrane potential to go back to normal. What was happening? It's kind of not shown here. But what was the first thing that causes the sodium potassium concentration to be at the balance at resting potential? What was the channel or pump that causes the membrane voltage to be at -70 in the beginning? It's our old friend again. Who is this? Sodium potassium pump. So at this point, you see now this button is available again. So basically between hyperpolarization, when everything is closed, till at this point, yes, you have some leaked channel that is open. So there are some small movements of it, but then it is taking the sodium potassium pump to restore that balance. You notice here, the potassium concentration before it lits up, it's less than 140, okay? Less than 140 millivolt. When it's at resting potential, it is 140 and 10 and 4 and 145. Before, it's not, okay? It's slightly different, but it's not. So during this period of time, called the refractory period, you can't stimulate the neuron at all, or this section of the neuron at all. Are you guys good? So in some ways, That's the detailed breakdown about resting and membrane potential. But we're going to look at that together. So take out your handout, definitely. Okay, so hopefully this records. Okay, so we're going to look down here. So a few things that is important. Make sure you highlight it. Make sure you highlight it. And we're going to add some onto the graph on the other side too. So first off, resting potential should, in order for this to send a signal, the resting potential have to go above a certain threshold level. Okay, and that threshold level is called threshold potential minus 55 millivolts. Okay, minus 55 millivolts. So when that happens, the membrane is said to be depolarized. Okay, depolarized. Going back to this slingshot or whatever example, I could release my grip on it, but then I have to release it enough before it will fire. Okay, that's like the threshold potential. So let's look at the graph on the other side. Okay, so there are a couple of things. So in this graph here, okay, I don't expect you to copy everything right off the bat, but we're gonna. So part A here, this will be the resting potential. Part B, what was that? Part B, this is called depolarization, okay? And during depolarization, sodium ion will rush in, okay? Sodium ion will rush in. Make sure you add those information. This is a very common question on a test where I could either show you the graph and kind of same thing, like A at point A here, what is happening or what is it called? Part B, at this graph, at point B, which of the following things is happening, or which of the following thing is not happening? Okay, so it is an expected question. Okay, so resting potential, depolarization. Okay, that's when sodium ion rushes in. Are we good? Quick. Okay, I'm gonna come back to this, so just wait. Now, when the electrical impulse is going through, it can go as high as plus 30 millivolts before it goes back. And the reverse, depolarization from negative to positive, and the restoration, repolarization, as electrical potential across membrane as nerve impulse propagated is known as action potential. Okay. Are we good? So in this case here, coming back to this graph. So this process here, this is being recorded. You can watch it later. During this process, so line X showing the process from it depolarizing till repolarizing, that's called action potential. That's a process of action potential. Now, part C here, in the video, they call it overshoot. And since the video is made by Harvard, I'll keep that. And the textbook calls it peak of action potential. So C would either overshoot or peak of action potential. And this process here, when it's going down, when the graphs start going back down, there's no number, so I'll put a Y here. It's basically repolarization. Repolarization. So during the peak or the overshoot, sodium gate ion closes, so the sodium ions stop flowing. Potassium gates start opening, so potassium rushes out. And that causes the depolarization. Are we good? Okay, I'm going to come back to this graph a little bit, okay? Now this here, this summary, uber important. Know it. That's an expectation for this course, okay? Very, very important. Now, this part here, it talks about the sodium potassium pump, which wasn't talked about earlier. It's maintained, the resting potential is maintained by sodium potassium pump. Remember in the video, it takes up about 20 to 40% of the brain's energy consumption. Okay. And by the way, the brain uses which fuel predominantly? I talked about it back in unit 1. Yes, ATP, but how did the brain uses what to get the ATP? It mainly uses glucose. So this is the part where like some people who are, what is it? From what I read, a lot of times bodybuilders or people who, yes? Say again? For the brain using creatine? Isn't that more muscle? I don't remember that part. The what? The brain cells also use creatine too? Okay. Okay. I will definitely look it up. But a lot of times in bodybuilders or I know some models, fitness models, when they're just before their photo shoot, they want to look really lean, so they cut out carbohydrates for a number of days, and that causes a lot of mood swing because that's partly dealing with this. They don't have enough of the glucose to have enough of that energy to regulate. Okay, it does messes things up. So resting potential, sodium potassium pump. We talk about the stimulus. So the voltage-gated sodium channel opens, sodium comes in. Sodium comes in, start depolarizing, less negative. When you have to get to minus 55 and more voltage-gated sodium channel opens. So before it hits minus 55, only some of that voltage-gated sodium channel will open. Once you pass that minus 55, much more of it. Okay. Now, after the sodium rushes in, membrane potential is reversed. Now it becomes more positive on the inside. So you call that action potential. At the peak of the action potential, about 30 millivolts, voltage gated sodium channel closes, voltage gated potassium channel opens. So potassium ion rushes out of the cell. So now the cell becomes more negative, it repolarizes. Okay. Now we talk about the refractory period. Basically, that period of time after stimulation, after action potential, before you can have another action potential again, or depolarization again. So refractory period, when channels rest between opening, it ensures one-way impulse flow. The membrane is said to be hypopolarized. This is due to the delay of potassium channel closing. Okay, delay of potassium channel closing. So if I look at the graph down here, again, so at point D here, that is hyperpolarization. Hyperpolarization. And this period of time, so between that until the time before it reaches resting potential again, this will be the refractory period. Okay. Now line O here, that's the threshold potential. Oops. Are you guys okay? Any questions? Yes. Yep. I'm gonna go back up there. So at this point, resting potential later on is restored by sodium potassium pump. So this is the part, if I ever ask you to describe the process of nerve impulse or describe the process of action potential, depolarization, the whole entire thing, this is the part, make sure you know it and be able to say it. Okay. Now, before moving, talking about propagation of the nerve impulse, how many of you have played with fireworks before? Okay. So you can remember when you're playing fireworks, you're lighting that fuse. So you light up the fuse at one end, the heat energy from that fuse part that is burnt causes the next part of the fuse to be lit up, and then it just keeps going, right? It's the same idea in terms of impulse propagation. So the depolarization happened here. Okay, the rest of this part is resting potential. The part just behind it, it's going refractory period, so it cannot do depolarization again. So in this case, the depolarization that happens here creates the stimulus that causes the next part to start depolarizing. Hence, the nerve impulse moves this way. As it moves that direction, the part that just had depolarization, just had the action and potential, it's going through refractory period. So it can only go this one direction, okay? So think firework fuses. Any particular question? No? So today, this is it. We're only talking about nerve impulse, resting potential, action potential, refractory period. Tomorrow, we're going to talk about synapses. Now, which is personally, I think, is the most fun part about the neurotransmitter, uh, this section. So, what I'm going to ask you guys to do, a couple of things. First off, so homework and classwork. So on textbook, page 529, number 2. So I'm going to show you here. Textbook 529, number 2. Basically, here there is a number of different membrane potential you are to describe. So what's going on at that point? What kind of movements of ion is moving, and what direction and why, or what causes it? Okay, those kind of things. Describe the movement of ion. That's one. Now, there are 3 short Edpuzzle videos I want you to watch. The first one is about chemical synapse, basically what we're going to be looking at tomorrow. Now, because synapse and neurotransmitter, it's quite wide-ranging in terms of application. So the second video is about SSRI. SSRI is a class of antidepressants. It's actually quite commonly prescribed antidepressants. Okay, serotonin something reuptake inhibitor. Okay, so this this antidepressant work by stopping the reuptake of serotonin, which is one of the many types of neurotransmitter. Okay, so this video will talk about how that works. Cocaine. I'm not endorsing use of illegal drugs. Okay, it's very expensive anyways. But cocaine and neurotransmitter is a very, very, very well studied example. So in this case, this video will talk about the mechanism of action. Okay, for those of you who are thinking about your lit review, like mechanism of action of a medication, or this is going to talk about how cocaine works. Okay, it it usually it messes with a neurotransmitter called dopamine. So basically, the dopamine pathway Basically, if you're ever studying pharmacology or anything that's talking about substance dependence or any even behavioral dependence things, it's usually involving the dopamine pathway. So it's very interesting. So there are 3 of these puzzle videos that I do want you to watch. Last but not least here, this is an optional, okay? This is an optional playlist. During the pandemic, I found this series of videos called Your Brain on Blank. Okay, it's actually done by a neuroscientist, and she would talk about various types of things that's happening into your brain. So while it's on alcohol, caffeine, breakup, social media, kittens, and I personally like this one the better, sleep deprivation. What happens? Okay. So this is not a required watch, but if it is one of those things, like if you're wondering something to procrastinate on, I would suggest watching that. Okay. So those are the things I want you guys to do. Any questions? Okay. Okay. So